The way your book introduces it is just by giving you the formula. The kinetic energy in a rotational system is given by the equation of 1/2 I omega squared. Again, I is the moment of inertia, and omega is your angular velocity. So, you might notice that this is very similar to normal translational kinetic energy, which is 1/2 mv squared. Alright, so as an example problem, number 2, we have a bottle that's going to be rolling down a slope. We know that the height of the slope is 5 meters. They tell you that the radius of the bottle is 0.56 meters. And it has the same rotational properties as a thin hoop rotating about its symmetry axis, which just means that its moment of inertia, I, is equal to mr squared. And it's asking, what is the linear speed of the bottle after rolling down a slope of height of 5 meters? Do you need to know the mass of the bottle? So, the way to approach this is we know that mechanical energy is conserved. So, the mechanical energy initially is equal to the mechanical energy in the final state. And the three main types of energy, mechanical energy, are potential energy, kinetic energy translationally, and kinetic energy rotationally. So the initial case for each of these, if you add them all together, is going to be equal to the final case for all of these. Now, when it's at the top of the slope, it's not moving translationally or spinning rotationally, so it doesn't have any kinetic energy or rotational kinetic energy. So those are going to be 0, they'll just cancel out. When it's at the bottom of the slope, it no longer has any potential energy, which is all that it started with. It's out of potential energy, so that cancels out, but it will have some translational kinetic energy in that it's moving translationally, and some kinetic energy rotationally because it'll be spinning. So that boils down to the potential energy that it starts with is going to have to be equal to the kinetic energy that it ends with translationally plus the kinetic energy that it ends with rotationally. Now, potential energy is given by mgh. Kinetic energy is given by 1/2 mv squared, and kinetic rotational energy is given by 1/2 I omega squared. We're going to replace this I with this equation since it has an m in it, because we want each of these terms to have an m so that they'll all cancel out. So we're going to just replace I here with mr squared, and that's still times omega squared. Now there's an m in each term, so if we divide everything by m, all of the m's just cancel out and you end up with g times h equals 1/2 v squared plus 1/2 r squared omega squared. And we're looking for the linear speed that the bottle acquires after rolling down the slope. So the linear speed, the velocity. We know g, we know h, it's 5 meters. This is what we're looking for. We know the radius, it's 0.56 meters, but we don't know omega, right? The angular velocity is not given, so it would seem like we can't solve this problem. But what we forgot when we were working on this problem in class was that omega is equal to the tangential velocity divided by r, where in this case tangential velocity is equal to the translational velocity because of what I was talking about in class. So we can rewrite omega squared as v over r squared. Now again, we know g, we know h, V is what we're looking for. We know R. Again, V is what we're looking for, and we know R. The only variable that we don't know is V. So you can solve this equation for V, plug in the numbers for each of the other variables that are known, and get the actual value of V. And that's how you solve the problem.